All right. Hey, everybody. So in the next series of videos, we are going to talk about a big idea in real analysis and a relatively challenging idea. So we're going to build it up bit by bit. The idea at hand is compactness and what it means for a set to be compact. We'll build it up bit by bit because the definition of compactness is reasonably challenging, involving these abstract collections of open sets. And so we're going to start there. So we're going to remind ourselves what a collection of open sets is. And this is something that we talked about back in chapter 3 when we were discussing openness. So as a reminder, a collection of open sets is a formal way to describe a set of sets in which each of the sets in the larger set or in the larger collection, each of those is open. A nice way to refer to these, and a way that we'll use often, is we will define the entire collection, so that's the set of sets, using the script F. And then we will use these sort of script O's to describe the individual open sets in the collection. So formally, our collection F is a set of these open sets O sub I. Here I is an index, so it's a way to refer to the individual open sets, and I is an element of the set capital I, which is the set of different indices. So let's go ahead and talk through a few specific examples. Okay, so for example, let's start with a relatively easy one. Let's talk about the set that contains 3 sets in it, right? So this will be a collection where capital F, or script F, is equal to the set containing, let's say, 0. The open interval 0 to 4 is one element. The open interval from 2 to 8 is another. And the open interval from, let's say, 7 to 11 is our third. Okay, so again, I could write this if I wanted as F is a collection of 3 different open sets, O sub 1, O sub 2, O sub 3, where very formally, O sub 1 is just defined to be this open interval, O sub 2 is defined to be this open interval, and O sub 3 is defined to be this open interval. And to use the notation from up here, I'm using indices 1, 2, 3, and so my set I, my set of indices, is just a set that contains 3 elements, the elements 1, 2, and 3. Okay, this is a collection of 3 open sets, and that's one example. Let's give a second example here that's just a little bit more complicated. Okay, our second example will be this. So our script F, right? This set, I'll say, will contain, let's say, 10 or 11 different open sets. And I'm going to jump right to denoting it as follows, right? This will be the set from 0 to I, such that our element I is an element of the set 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, let's say 11, to give ourselves 11 sets. Okay, and this looks a little confusing at the moment. In particular, I have sort of like the set notation inside the other set notation, but formally, this is going to be 11 sets. It'll be the open, this will be a set of 11 sets, or set of 11 open intervals. The first open interval is the interval 0 to 1. The next open interval is the interval 0 to 2. The next open interval is the interval 0 to 3, and so on, up to the open interval 0 to 11, right? And again, I could formally write this as this, F is the sum of O sub 1 up through O sub 11. So 11 open sets, and our our set of indices, in this case, is going to be the set 1 to ... up to 11. So each of the numbers 1 through 11 here is an index describing a particular open set. Okay, let's go, let's do one more example. Let's make this one even more strange or even more challenging. Okay, this collection of open sets will contain infinitely many open sets. So this will be all sets of the form, let's say, x minus 1 to x plus 1. So open intervals of the form x minus 1 to x plus 1, such that my x is an element of the closed interval from 1 to 10. Okay, so, right, again, this is going to be a set that contains infinitely many, in fact, uncountably infinitely many open intervals. X is my index, and x is allowed to be any real number between 1 and 10. So that includes the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That includes the number 3.5. That contains the number pi. That contains the number square root of 2, right? That contains uncountably many numbers, uncountably many real numbers in between 1 and 10. And for every single one of those numbers, the associated open interval is the interval from that number minus 1 to that number plus 1. And so I could write this using our, sort of more formal notation. I could write this as F equals the set of all O sub x, right? Because here x is my index instead of I. O sub x such that x is in the interval 1 to 10. And again here, my indexing set, it's no longer just a finite list of numbers, right? My indexing set is equal to the uncountably infinite set from 1 to 10. Okay, great. If I also wanted to display these visually, right? I mean, again, just to make sure we're all on the same page, I could display these visually as follows. Okay, so here I've drawn 3 different real number lines, one for each of our examples. And what we'll see is that in this first example, again, there were 3 sets in our collection, which I will sort of draw just hovering slightly above the real number line itself for clarity. We have the first set, O sub 1, that's going to be the open interval from 0 to 4. So that will be sort of this open interval right here. That'll be my O sub 1. Second open interval, that will be O sub 2. That will go from 2 to 8. And so that'll go way up here. That's O sub 2. And then O sub 3 is going to go from 7 to 11. That will be this set here, right? So again, we've got O sub 1, O sub 2, O sub 3, and this is a collection of 3 different open intervals. Okay, next up, we've got 11 open intervals, each going from 0 to I, right? So we've got our first open interval is going to go from 0 to 1. That's going to be O sub 1. Our second open interval will go from 0 to 2. Our third open interval will go from 0 to 3. And already I can tell I'm going to have to stack these more closely on top of each other if I want to get them all to fit in this picture. So maybe we'll just start superimposing them. So we've got, that's O sub 1, O sub 2, O sub 3, O sub 4, and so on and so on. We get this nice, lovely little picture, messy picture that I'll cut ahead to the end to. All right, and there we go. We see we have 11 open sets. That's 11 open intervals in this case. You know, they're covering a lot of the same ground, especially over here, but we consider each of them as an independent element of our set of sets. Finally, we get to our final example, which we will not be able to draw in good faith because there's uncountably many sets there. But let's draw at least a handful of the sets to get a sense of what this looks like. So again, these are indexed by x values between 1 and 10. So that includes, for example, O sub 1, that is indexed by the number 1, and that is the set that goes from 1 minus 1 to 1 plus 1. So that's the set that goes from 0 up to 2. So the open interval from 0 to 2, that's my O sub 1. I could also talk about O sub 10, right? O sub 10 will go from 9 to 11, so that will be O sub 10. But then we've also got all of these other ones in between, right? So I mean, we could talk about integers, so I could say O sub 2 goes from 1 to 3, right? And that's O sub 2. But I could also talk about O sub pi. O sub pi is going to start right about here at 3.1415, etc. It's going to start at pi. And so O sub pi will go from pi minus 1 up to pi plus 1, and that will be O sub pi. And so we see there will be uncountably infinitely many of these little intervals, each of which is of length 2, right? And they're all sort of stacked more or less on top of each other, and each of them is indexed by the point that's directly in the center of them, right? And I'm going to stop my drawing here in just a moment, but you can imagine really there are uncountably infinitely many of these stacked in there. Okay, so this video dealt with how to define collections of open sets and how to sort of organize the notation. In our next video, we're going to see what we can do with these open sets. So I'll see you next time.